Hello, everyone. It's my great pleasure to introduce Tian Li, who is receiving her Ph.D. degree in computer science at Carnegie Mellon University, working with Virginia Smith. She will join the Computer Science Department and Data Science Institute at the University of Chicago as an assistant professor in 2024. Her research interests are in distributed optimization, federated learning, and trustworthy ML. Prior to CMU, she received her undergraduate degrees in computer science and economics from Peking University. She received the Best Paper Award at the ICLR Workshop on Security and Safety in Machine Learning Systems, was invited to participate in the EECS Rising Stars Workshop, and was recognized as a rising star in machine learning data science by multiple institutions. Again, welcome to our webinar series, Tian. The floor is yours.
Thanks, Hadi, for the nice introduction. And thanks everyone for attending. So today I'm going to share some of my recent research on tilted losses in machine learning. So I'm going to start from, and this is joint work with my awesome collaborators, Ahmad, who was at Facebook and now has a Google research, and Mas and my advisor, Virginia. So I'm going to start from federated learning, which is one of the major applications and areas that I worked on a lot during my PhD. So we know that machine learning heavily relies on data in various applications. And where does the data come from? They can come from the devices or clients or sensors. And more frequently, they are generated by and siloed across not just one, but networks of many remote devices or organizations. So for example, can imagine that we want to jointly train a model to predict the next characters across a number of smartphones. But sending sensitive and real-time user data to some data center may not be allowed, or sometimes they can be very costly. So it's important to enable access to such large amounts of data without moving all of them to one central location. So learning across networks of decentralized data while keeping all of them local is very important because it can protect sensitive user data and protect data ownership. You can also avoid expensive or even sometimes prohibited raw data transmission, and then boost the effective sample size by collaboration. So one critical framework that supports data sharing is federated learning. And it has been deployed by a number of service providers and real-world applications in different areas. So for example, in the cross-device setting where we learn over remote devices, and example applications include speech recognition on phones and predictive maintenance across sensor networks. And another popular application scenario is the cross-silo setting, where we jointly learn over isolated silos or organizations. So usually the scale or the number of clients is less than in a cross-device setting. So for instance, we want to do tumor detection across 29 institutions and detecting money laundering across banks. So usually there's a central server and a bunch of devices communicating intermediate information with the central server periodically to jointly learn some statistical models. Okay, so at first, it may sound like it's very similar to the distributed learning setting where we fit data across distributed data sources, fit a model across those data sources. But there's some kind of unique challenges and properties of federated networks. Yeah, so first, the entire systems can be very heterogeneous due to the variable hardware of the devices, the network connections, different battery powers, and so on. And then each device generates local data following a local distribution, which can be very different from each other. So user data are not identically distributed. So you can imagine that different users may use their phones, different styles, right? So this data heterogeneity issue can affect the training pipeline a lot. And communication is a real bottleneck in this setting compared with the communication in data center environments where the machines are well connected, right? So here, sometimes we do learning over wireless networks, so it can be orders of magnitude slower. And then privacy is a major concern. So federated learning takes the first step towards protecting user privacy by minimizing data exposure in the system. Means that it never transmits the raw data between the devices or from the devices to the server, but it's not inherently secure or private. And usually we need additional mechanisms on top of it to guarantee some specific notions of privacy or security. We also discuss some of the challenges and recent methods in the survey article. So today I want to focus on the issues of heterogeneity on fairness in federated networks. So starting from that, let's look at the canonical formulation for federated optimization. So this is this classic empirical risk minimization objective. So we want to train a model W to minimize the finite sum of the empirical losses across all the devices. So here F is the local loss or local empirical loss for each device. So here we have N devices in total. And then PK are some predefined constants for each device K. For example, that can be set to be the number of, or the fraction of the number of local samples on that device. And then because of heterogeneity, minimizing such an average of empirical losses may disproportionately advantage or disadvantage the performance on some devices. So you can imagine that we can have a model that has very good average performance, but it can perform catastrophically on a subset of the network because some clients may be different from each other. So for example, here we show the test accuracy distribution of all devices from a model trained on a real-world federated dataset. We see that a small group of devices or clients suffer from low accuracy. And the question we want to ask is, can we encourage a more fair or a more uniform distribution of the model performance across devices? And the motivation is that from a service provider's perspective, we would like to offer consistent quality of service across all the participants in federated networks. And so here, the fairness definition is a little bit different from the classic fairness definition in the machine learning literature, where they focus on this statistical independence between predictions and protective attributes. But here we define fairness as the uniformity of the performance distributions. And so this is also known as representation disparity in previous literature. And then the goal is to reduce the performance variance by increasing the performance on the worst performing groups. Okay. And so instead of minimizing that empirical loss, we propose a new objective inspired by fair resource allocation. So our objective is called Q Fair Federated Learning, or QFFL for short. So it minimizes an aggregate reweighted loss parameterized by Q. So Q is some positive value larger than 0, such that the devices with higher loss F are given higher relative weight in the overall objective. And so called a fair resource allocation objective. And it's inspired by alpha fairness for fair resource allocation in wireless networks. And what's nice about this framework is that it enables flexible fairness accuracy trade-offs through a tunable parameter Q. So when Q is equal to 0, we see that this objective recovers the vanilla ERM objective. And if Q is large enough, it will optimize for the worst case loss, so reducing to the existing minimax fairness objective. Okay. But what's nice about this objective compared to minimax fairness is that this trade-off, this Q offers by ranging from 0 to positive infinity, can be more desirable in terms of both the computation efficiency and then the properties of the solutions. Yeah, so going back to the previous example, see that the model can fail on some devices if we use the baseline objective, which is ERM. And by using QFFL, we can maintain the approximately the same overall average accuracy while reducing the variance. And we see the performance of the worst performing device has improved dramatically at the cost of potentially reducing the best accuracies a little bit. And then we can see similar improvements across other data sets. Yeah, so we also created some benchmarking tools with natural partitions across clients to simulate federated environments. And across a set of benchmark data sets, we can observe almost half of the variance reduction in terms of the test accuracy across all the clients, while maintaining the same mean accuracy. Yeah. And then we also do this across all the other data sets, and those are the detailed results. We have the synthetic data set where we can manually control the statistical or data heterogeneity across the network. Had this vehicle data set, which was the result I showed before, and then set 140, which is the Twitter data set. Do we perform a sentiment analysis across those tweets? And then each Twitter user in that case is a client or a device, and then Shakespeare data set. We observe that, again, the variance is, the accuracy is cut by, the accuracy variance is cut by almost half. Okay, so more generally, the case study I presented before is specifically focusing on federated learning. And we talk about how empirical risk minimization can disadvantage some parts of the clients. And then more broadly, this issue of unfairness against underrepresented populations is not specific for federated learning, right? So essentially, this limitation comes from the deficiencies of ERM itself for general machine learning problems. Okay. So this is an ERM objective for general machine learning, and there are N training samples, and then Xi is the data point that can also include label information, and then W is the model that we want to fit. And so minimizing this average empirical loss is very standard in machine learning because it has nice statistical properties, but it may perform poorly when the average performance is not an appropriate measure. So which means that when the training and testing distributions are not the same, if we just minimize this empirical loss over the training data, the test performance may be bad. So for instance, if we have minor subpopulations in the training data and we want to be fair to all the populations in test data, and we might have corrupted data or imbalanced data or some other forms of distribution shifts in the training process. Okay, and then inspired by similar intuitions from QFFL, we propose a more general objective, which we'll call tilted empirical risk minimization, or TERM for short. So instead of minimizing the average of the losses, so tilted ERM is minimizing the exponentially tilted average of the losses. So we see that in this new objective, T is a hyperparameter that controls the impacts of individual losses. Okay. So similar as QFFL, when T is a positive constant, is larger than 0, the large losses will be outweighted exponentially in the overall objective. But different from QFFL, here we also allow for T, this hyperparameter, to be negative. So when T is negative, small losses will be outweighted. And I'll talk about this later, is that focusing on small losses can prevent overfitting to corrupted data. So intuitively, what does QFFL do? So in the left figure on the toy problem, we see that this is a linear regression problem. If we view the sparse points on the left as some underrepresented data that we would like to fit, we can use term with positive T's, so the red lines, to highlight them or to fit the sparse points. And however, on the other hand, So if the points on the left are some outliers that we would like to ignore, so we only want to fit the majority of the data on the brown points, and we can use term with negative t, so the blue lines, to ignore those points on the left and only fit the major points there. So in summary, we see that at a high level, term can highlight outliers to promote fairness or suppresses outliers to promote robustness with a single child hyperparameter. So I will talk about some of the nice properties of the term objective. By ranging t from negative infinity to positive infinity, it recovers a family of objectives parameterized by t. So in terms of the average loss, when t is close to 0 in the objective, it will reduce into the classic ERM objective. So the objective is the average loss. And when t goes to positive infinity, it recovers the max loss. And when t is negative infinity, it recovers the mean loss. So I'm showing the max loss, average loss, and mean loss on this toy problem with only 3 data points. And the loss functions are shown in the title of this figure. And for intermediate values of t between negative infinity and positive infinity, term provides a smooth transition between mean loss to average loss and to max loss. So another motivation for this objective is that it not only generates different solutions from ERM or different from minimax objectives, but it can also have convergence benefits relative to other risk-averse measures, so other non-ERM objectives. So we will also talk about that later. Yeah. So how do we interpret this objective? So another way to view term is that we can look at the gradients of this objective. If we directly compute the gradients over this tilted objective, we see that the overall gradient is a weighted average of the individual gradients with respect to the model parameter theta. And then, yeah, so here may be some abuse of notations. So before, I think W means the model parameters, but here theta is the model parameters. And WIT theta is some constant, some weight on the data point I under the model parameter theta and then the child hyperparameter t. So we see that this weight is exponentially proportional to the loss values, which again is consistent with what we observe in the objective. So when t is positive, we can increase the weight on the large losses to maybe highlight those underrepresented groups which may have a large loss. And then when t is negative, we are downweighting the large losses. So if some of the data points are malicious, corrupted, and then they usually have a large loss because the model will usually fit the easy samples, so the clean samples. And then we are able to ignore the noisy points in this case. Okay. And then we also study other properties such as the trade-offs between the losses. So when t is positive, as t increases, we prove that the average loss will increase and the max loss will decrease and the loss variance will also decrease. So this gives us a different point in the bias variance trade-off curve, right? So it's essentially saying that we are increasing the bias by reducing the variance, and potentially we can get better generalization. And when t is negative, we show that when t increases, the average loss will decrease, and then the mean loss will increase. Right? So it's always the average loss will be minimized if we use the ERM objective, because that's what it optimizes for. And then when t is negative, if t becomes more and more negative, and then the mean loss will be smaller. Okay. Another important connection between the term objective and other previous objectives is with this distributionally robust optimization. So distributionally robust optimization is also another type of non-ERM objective, where instead of minimizing the average loss, it minimizes the mean loss over the worst case loss. And then the worst case loss is constrained by some uncertainty set around the empirical distributions. And we proved that this term objective can be viewed as the dual form of this a slightly different variant of DRO with a max entropy regularizer. And then this uncertainty, so instead of having an uncertainty set modeled by some KL divergence ball, we are putting this KL divergence ball in this regularization part. And then this is also known in some previous results. And so you may wonder, does term have some regularization effects? And then yes, it can also be viewed as a regularization to empirical risk minimization. Can rigorously write out the form, can show that term is basically ERM plus some KL divergence-based regularization term, where this W, again, is the weights for in front of each sample, and which is exponentially proportional to the loss values. And then here, U is some uniform vector. So this is KL divergence between a uniform vector and a tilted loss vector. And then this constant is 1/T. We see that when T is 0, basically it just minimizes this KL divergence to encourage the loss to be uniform. And then when K is when T is very large, it basically enforces this uniform distribution. And then when T is close to 0, it will recover the ERM objective. So term solutions also approximate solutions of quantile losses. Right? So there are various approximations that term can offer. And how do we define the quantile losses? So we have a finite sample. So assume that the total number of samples is n, and then we have the losses for each sample f, xi, theta under the parameter theta. And the kth quantile loss is defined as the kth largest individual loss from this set. For example, medium loss is the n/2 quantile loss. And we show that like both theoretically and empirically, term solutions can approximate K loss solutions and K from 1 to n. So for instance, in this point estimation problem, the sample, the geometric medium is shown in the orange points there. And then it's not in the term solution. It's not in the term solution set, but the term objective can generate an approximate solution to the geometric medium. And those kth quantile losses are usually very hard to optimize. For instance, even this medium can be difficult to solve, especially when the dimension is high, but then term can offer some approximations. And then how good that approximation is, so we define this Q gamma theta as the quantile of the losses that's larger than some threshold gamma. So this fraction of the losses larger than gamma is some value between 0 and 1. And we show that some function based on term, which is shown on the right-hand side of this theorem, can offer an upper bound of this fraction of the losses that's larger than gamma. So basically, if we solve the right-hand side, we can guarantee that the left-hand side is smaller than that. And then the right-hand side is relatively easier to solve. And also by kind of treating t as a variable, as opposed to a hyperparameter in the previous discussions, we also provide a way for automatically tuning t. Okay. And based on this quantile losses, we can also introduce value at risk, which is known like for many years, especially in the finance and or insurance literature and operations research. And then so value at risk with confidence alpha is defined as this. So we want to minimize some risk value such that and then this figure may be more intuitive. So we want to minimize some risk value such that the risks larger than this value gamma is at most alpha. And this is a very fundamental tool in operations research to control the risks. And it's intractable to optimize. It may even be non-continuous. And the term leads to a tighter approximation to this value at risk than some other existing approximations, such as conditional value at risk. Okay. And then in this figure, we empirically show like on this toy problem, how tight the approximation is. If we want to look at the approximations of value at risk. So x-axis is the alpha value. So the alpha value defined in VAR. And the y-axis is the risk values. And then here we are looking at the risks of different objectives. So VAR is something that we would like to optimize as the end goal. And then because it's very hard to optimize, there are different approximations. Previous approximations include CVAR and EVAR. So this conditional value at risk and entropic value at risk. So they are both non-ERM type of objectives, risk-averse objectives. And then we propose a different objective, tilted value at risk, which is denoted as TVAR here in the yellowish line. And then we see that in some regimes, especially when alpha is close to 1, we can offer a much tighter approximation to value at risk than CVAR and EVAR. And then it's easier to solve. And then lots of the details are discussed in the paper. And then what's the operational meaning of the regime where alpha is larger or is closer to 1? So if we go back to this definition of VAR, we see that when alpha is close to 1, it basically optimizes for the mean loss. So this is very important for robustness applications where we want to focus more on the small losses. Okay. Okay, before I described how we got to the term objective, the motivation, by some case study on fairness problems in federated learning. And then I also talked about various properties of the term objectives to help us better understand the influence of the T hyperparameter and also how term connects with other previous risks, such as distributionally robust optimization and conditional value risk, OVR. And then another type of question we want to ask is how do we solve term efficiently? In the next, I will talk about that. So look at this term objective. We can show that if the original losses F is smooth, and then this entire objective term is smooth for all finite t, except for when t is positive infinity, which basically minimax is not smooth. And then if when t is convex, when f is convex, and then for any positive t, the term objective is also convex. So that's the properties if we think about solving for a term. And then in the full batch gradient setting, it's relatively easy to solve term because we just compute the gradients over the objective, right? And then the resulting gradient will be a weighted average of the local of the individual gradients. Okay, so these are the weights, and oh, here W is the model parameters. And then we see that the weights are exponentially proportional to the loss values. But if we want to run term in the stochastic setting, so if we want to run SGD, for example, on this term objective, in order to get some unbiased gradients, we need to estimate the denominator of the weights, which will involve evaluating all the losses for each sample. So each step of SGD will cost ON, where N is the total number of samples. And this is too expensive. How to mitigate that? We just do some moving average to estimate the denominator of the weights. So the moving average can be like a linear combination between the previous estimate and the current like sum of e to the power of t times f in the current mini batch.
Warning in progress.
This will give a biased estimate, but we are able to show that it can still converge under this gradient. Okay, and the takeaway is that despite having so many good properties, and term is not complicated at all. It can be solved with a simple modification to standard ERM solvers. Okay. And then what is the convergence rate? So for analysis purposes, we sample 2 independent mini batches for estimating the weights and updating the parameters separately. And the rate is as follows. In the strongly convex case, where we have e to the power of tc times t over the total number of iterations t, and the rate is this. And in the possibly non-convex and smooth case, our rate is basically square root of 1 over t. So we see that they are almost the same as classic convergence rate of SGD, except that there is an exponential term, like constant, if t is bounded in the rate. So an open question is how do we get rid of that, or is it possible to get rid of that? So basically, to understand the scaling with t as t goes to positive infinity, because in this case we are showing a result with exponential scaling, but in practice we observe something much better. So when we do our experiments, and it's still an open question to understand the actual scaling with t under our algorithms. Yeah, so we own some synthetic data sets. We look at the convergence of t as the number of iterations. So t here, when t goes to positive infinity, we are using some red lines, and then for negative t's, we're using some blue lines. It's the same as before. And we see that the purple line corresponds to the convergence of ERM objective. And then this, when t is very, very large, the convergence will become much worse. And then the convergence of this non-convex objective when t is smaller than 0 is reasonably good. But in all our experiments, term runs within 2 times iterations of ERM. And this is just to show like the convergence of term 1T is very, very large on a synthetic data set. Okay. So next, I'm going to talk about applications of tilted ERM. Because it's a very general framework and can be applied to a wide range of machine learning problems in different domains. First, when T is negative, we can do outlier mitigation, robust regression, robust classification. And when T is positive, we can apply term to different fairness-based applications like to address class imbalance, fair PCA, so principal component analysis, and then variance reduction. And then in this objective, we can even do hierarchical tilting by using both positive and negative T's at different levels to achieve fairness and robustness jointly. And what's surprising is that despite the simplicity of term, we observe competitive or even superior performance of term compared with application-specific state-of-the-art approaches designed specifically for those applications. And the next, I will discuss some of them as an example. So for example, fair PCA, we are using term with positive T's. So the goal of fair PCA is to encourage equal construction error after this PCA algorithm. Okay. So L and H are 2 groups, and U are learned low dimensional features. And the goal is for the reconstruction error, denoted as the loss here, to be similar across the 2 groups. And we see that on the credit data set, if we use standard PCA, there's a large gap between the losses on high education and low education groups. So it's not fair. And then term can recover a recently proposed minimax fair solution with a large T. But at the same time, can offer more flexible trade-offs between performance and fairness by encouraging fairness in a less aggressive way. Okay. And then we also looked at an application of class imbalance. So here we have 2 classes in the sampled from the MNIST dataset, 4 and 9 digits. Look at the test accuracy as we manipulate the common class ratios. We see that term matches state-of-the-art methods without additional cleaning data. So term performance is the blue points here. That's okay. So for negative T's, we can apply term for robustness applications to get rid of those noisy samples. In this drug discovery dataset, we manually created some noisy labels following the setup of some previous works. And we show the test error as the noise levels increase. But when we have 20% noise, term is roughly as good as other loss functions like L1 loss, which is inherently robust to the outliers, and Hilbert loss, which is also a very classic loss function. And some other recent methods like CRR, I think, consistent robust regression based on, and then STIR, I think those are based on some hard thresholding, these methods. And then when the noise level increases, especially when we have 80% of the noise, term is much better than the other baselines. Let's look at another robust classification problem. So we look at the applications of noisy annotators for crowdsourced. So those noisy annotators will create some noisy labels for the training data. And here we're looking at the CFAR10 dataset. So this having 80% of the labels produced by low quality annotators will dramatically decrease the test accuracy of the trained neural network. And by applying term, with an active case, so here we tilt the losses grouped by the annotators, and we are able to achieve the same accuracy as Gini ERM. So here, Gini ERM means an impractical upper bound, so that is directly training the model by removing all the noisy samples. And term also outperforms previous strong baselines on this problem. Yeah. Okay. And then we can apply tilting at different hierarchies of the data set to achieve both fairness and robustness. Here we create different scenarios where we have both imbalanced data and noisy data. And we see that only term is able to handle both at the same time, while focal loss can only handle imbalanced data, and robust regression risk can only handle imbalanced data, and a generalized cross entropy loss is only able to handle noisy labels. Okay. And then I showed some of the example applications that we presented to study the properties of term, but in our paper we have other applications or more detailed analysis of those algorithms. And the takeaways of term is that, so first is a simple baseline for many problems in machine learning, like fairness, robustness, cost imbalance, and so on. And then it provides a trade-off between mean loss to max loss and ERM. And then this objective can be easily solved at scale, and they can be easily used to approximate other common approaches. I should also mention that the idea of tilting is not new, so it's coming from the exponential tilting literature, which has been studied a lot in statistics and information theory. But here in this work, we look at tilting for machine learning. And what are some of the open questions here? One is to study the generalization properties of term with respect to T. But while we have shown that term can reduce the variance, but at the same time, it will increase the bias. So it's still not clear how specifically it can improve generalization, though in our experiments, we observed that it does help. And then more detailed or systematic principled comparisons between term and other large-scale DROs, distributionally robust optimization solvers. And additional applications of term and solvers for our proposed tilted valular risk objective, so which is a variant of another objective based on term that may have independent interest. And then the code of all the experiments is open source online, and we also wrote a blog post on that. And if you want to read the papers, we have a conference version and the recent JMR version on my website. Thank you. I'm happy to take any questions.
Great.